Hey, welcome to the introduction to a unit of work called Models of Growth. And what might that mean? Over here, models of growth. Oh, what's that? People who show off new fashions? I don't think so. Here we mean mathematical models, where what we're going to try and do is to find a mathematical description for practical situations around the screen here. Have a look. Is there a mathematical description? Maybe a graph, a sequence of numbers, a formula to describe how something is growing or changing in different ways. And does anybody recognize this guy here? And I'm going to introduce you to him. He's long since gone. He's a Greek guy called Pythagoras, who was a mathematician and philosopher who considered the world to be number. In other words, there are so many things in nature. Here's a couple of examples where the patterns can be described by number. Okay, that there is some mathematical structure to our world. All right, well, that's the idea. We're going to have a look at all of these things around the screen here and see if we can describe what's going on and describe the pattern or get a mathematical model to work out how it's going to grow and develop if we kept going. Okay, if we made more tiers on this stadium here, what would happen? How many seats would we need, etc., etc. Okay, so let's go down and let's start some stuff here and see what you think. So the screen clippings here are from Hayes and Harris Publications, and we're going to call this first type of modelling sequence modelling, or number sequences, to describe a pattern that we might observe in a building like that brick wall or something like that. So here's our definition. A number sequence is a set of numbers, so it's a sequence of numbers one after the other, defined by a rule for non-negative integers. Wow, that's a mouthful. What does that mean? So in other words, it means we're going to have several terms, the first term, the second term, so they won't be negative, but we're going to have the first one, the second one, and the third one in position. And then we're going to have a value, a set of numbers in the first position, second position, third position. Let's see that more clearly with an example, I think. We come down here, here's our brick wall that we're building. So here's our first row, second row, third row. Can you please notice that they can't be negative and they would be whole numbers. So we're going to put these bricks out. So the first number in the sequence is 3. Then there's, what's the next one? 4 in the next, 5 in the next row. Can you see that we are devising a mathematical model here, and we could make it keep going down there, and this would be the first term, call it n equals 1. This would be the second term. So these along here, these numbers have to be whole numbers and not negative. They're the number of the term. So we can say, hey, what's the dude here in that position? And the number 7 is the 5th term in this sequence. And that's our beginning, isn't it? To describe the mathematics of this, or to make a mathematical model of what's going on there. And you can see where it's leading. We may be able to predict what the 20th row would need in terms of bricks. Okay, so get the idea. Come down and look at something else from the screen there from before. That's the stadium one. Okay, so let's have a look. Building this stadium, and it's circular, and we're going to try and construct seats like this. And so we would have seats in row 1, however many there were, then row 2, row 3, etc. And we're going to try and draw up a structure so that it tapers like that. So we want the number of seats in this row, and how would they increase, and so on. So that's an important mathematical model. And this would be what? The first term, so call it n equals 1. They're just sneaking up on you here with the n idea. N is the number of the term in this work. So n is 1, n is 2, etc. And you might want to say, well, how many seats are in the 50th row? Will there be 50 rows? See the idea? So modelling at this level now is setting up a sequence of terms and trying to see the pattern in it. And that's our mathematical model, our mathematical description of the practical situation. Come down, there might be one that you recognise here from more junior maths. we've got $1,000, then it's 1,070, 1140. So the first term is n equals 1, n equals 2, etc. And what does this look like to you? It looks like money in the bank. Hope you got some of that. Pretty hard to get in the bank. Okay, so compound interest, I think, isn't it? It's growing all the time, and you're not taking any money out. So can anybody say what that would be then? 1,000 grew to 1,070. What would be the interest rate? Well, you've got 1,070 is 7% of 1,000, isn't it? So we are making this grow by 7% each time, or multiplying by 1.07. Have you ever seen that? Okay, so that's interesting. And our sequence here is being generated by going from one term to the other by adding 7%, or a constant multiplier of 1.07. That could be handy in looking at what's going to happen in 10, 15 years. All right, okay, so I hope you've got some idea now. Let's go and do some of the mathematics of it. And that just skipped a little bit down to here, so let's come back there. Okay, the general term. So in other words, we're going to try and describe further up the sequence of numbers what the term is likely to be. And there's a notation for it, this one, or this one. And generally we use little t n. So t1 would mean the first term, that implies the first term. T2 would imply the second term, etc. So we want maybe after 15 years, the 15th term. That's what we're going to try and say. What is the 15th term? So this is T1, or the value of T when n equals 1, first term, T2, or the value of the term when it's in the second position, n equals 2, and so on. So we want to find a formula for that, because that could be valuable, couldn't it? Once we detect the pattern in the sequence, then we could make a formula and predict what's going to happen further down if all the things were the same. But just remember, we're extrapolating then, and we're extending outside our initial pattern, and we'd have to make sure that there's all the conditions held. Just a little question for you as we go through. What might happen if this is compound interest? Why might it be hard to reliably, with a formula, with a mathematical model, predict what would be happening after 15 years? Can you think of something? Can you think of something? All right. Well, it's the interest rate change, isn't it? The interest rate could change quite dramatically as it is these days. And therefore it might be very hard to make a mathematical model that held for very long here. But we could still use it to predict and see if everything did stay the same, what would happen. So interesting stuff. Okay, come on down now. Let's just get rid of that and see what we think about this example. So again, screen clipping from Hayes and Harris Publications. So it'd be good to have a look at that in their book. Okay, so let's graph the first 6 members of the sequence there. Okay, so it's just seeing if you've got the jargon now. So the first term is n equals 1. So put 1 in the n hole there. 11 take 2 times 1. 11 take 2 is 9. Put n is 2 in here. So it's 11 take 4 is 7. Get the idea. So this little, what we call a subscript here, is a label, sub meaning under, submarine, under the water, subscript under the writing, under the script. So this is a subscript. It says that this is the n equals 3 term, or the third term. So you've got an n number, and then you've got a value for the term. So here you'll put the n in 11 take 2n, and so on. And then we could plot it. Just make sure you clearly label the n and the tn values and plot it out. So come along here, 1 is 9, term 2 is 7. And you can see what we usually describe here in this mathematical model, because this is now a graphical model, isn't it? This is a graph. Okay, so, or graph if you want, be consistent. So here you can see as n increases, Tn actually decreases. Okay, so this is a convention, by the way. This is called the independent variable, and the other one's the dependent variable. We always discuss behaviour coming along the independent axis, increasing in the independent axis, just for value on the independent axis, just for consistency. So if we say something's increasing, we know we're discussing its value as we go this way to the right along the axis with the independent variable, which is always going to be the horizontal axis. We always put it on the bottom there. So that's a little bit of convention. So we all are on the same page in terms of talking about increasing or decreasing functions. All right, so that's something we can do. What's another one? Let's do another one, get the hang of it. There's a power here. So each term is generated by raising 3 to the power of 2 take n. Let's do T1. So that's 3 to the 2 take 1 is 1, 3 to the 1, that's 3. T2 is 3 to the, what's this now? 2 take 2 is 0, so that's 1. T3 is 3 to the 2 take 3 is neg 1, so it's a third. Just remember the power rules here. Right, just a little bit of revision. A to the neg n, the negative exponent, means 1 on a to the n. And so that's clearly decreasing. This is actually what's called an exponential model because the value of n is in the exponent or the power. We're going to be doing some of that later on because there's quite a few things in everyday life that follow an exponential model, either decreasing or increasing. Okay, so get the idea. We want to get our head around all the different mathematical ways we can describe what's going on with sequences. We can have a sequence of numbers, we can have a graph, and we can have a formula. Okay, so we have all of those things. So let's go down and give you a go now. And so here's your little set, 2A1 from Hayes and Harris book there. So I want you to try to do the first 6 members. I think you should do all of them, because as you can see, the formulae are quite different from each other. And then answer this question as we move, as I said to you, from left to right across the graph. What's the sequence of numbers doing? Are they going up or coming down? And this is always the convention. We move to the right along the horizontal axis, the axis where we've plotted the independent variable. That's a mathematical convention. All right, now pause the presentation and have a go. I'm going to show you the answers now, and you might, as you do one, toggle forward and just check that it's right. Don't do all of them and find they're all wrong. Don't perpetuate an error. Okay, I'll show you the answers now. Okay, so here are some answers for A and B. Let's go down to C and D. And then E and F. And question 2, talking about whether they're increasing or decreasing. So check that. Check with your classmates and have a discussion, and with your teacher as well. All right, let's go on and have a look now at another example. Here's a bit more complicated one. We can see the mathematical model we've used here as a formula to describe the sequence. So let's put, here it is, 1 in the formula. So put 1 in there and there. You'd have 3 over 4 is what it would come to. T2, putting 2 in these positions now. So it's 5 over 5 or 1. Okay, you get the idea, and then we're going to draw the graph as a nice mathematical description or model of what's going on with its sequence of numbers. Okay, so here's yours, a little bit different here. List and graph the first 6 members of the sequence given by that. Just be careful with -1 to the n. Just remember, when a negative power is raised, a negative number, is raised to an even power, you get a positive. If it's raised to an odd power, you get a negative. All right, so pause it and have a go. I'll go and show you the answers now. So come down here, hang on, get rid of that. And come down here now. And there we have question 3A, and we'll just try and sneak in B. Yep. And then C down there. All right, okay, interesting patterns there. Can you see here, because of that negative sign, some are positive above the axis and some are negative below the axis. Did you get that one? All right, let's go down and do some formal work now. In this course, we're not doing very complicated sequences. There are only basically 3 types. So the first one is arithmetic sequence. And here's our definition. An arithmetic sequence is one in which each term differs from the previous one by the same fixed number. So it either goes up by the same amount each term or down. You could have a positive difference or a negative difference. So let's have a look here. Let's look at this sequence, 2, 5, 8, 11. What's happening there? Well, we can say it's going up by 3 each time. Okay, so that's our first little model. So it's arithmetic because the second term minus the first is the same as the third term minus the second, is the same as the fourth term minus the third term. Do you get the idea? So we've got a common difference, call it D, if you like, of 3. Just remember, it's the term differing from the previous one. So it's the idea of second minus first, and then third minus second. Okay, that's important, because if we don't follow that convention, people will be doing it backwards. It's not the first minus the second. Okay, it's as you go to the next term in the sequence, you minus the one before and see what it's going up or down by. So here it's got a difference of 3. Let's look at this one. 31 going to 27, it's gone down by what, 4, and this has gone down by 4, this has gone down by 4. So you always take it the second term minus the first was 4, and the third term minus the second, oh sorry, I said 4, oh it's negative 4, isn't it? Oh, it's going down, so should we get that right? So 19 take 23 is again going down by 4. So you could have a difference which is negative. So it's a decreasing sequence. Okay, starting to get the hang of this? So it's a fairly simple idea, but I want you to go slowly through this and get your head around it. All right, so come down and let's have a look at some definitions here. The algebraic definition of an arithmetic. We don't say this is arithmetic. It's arithmetic. So it's, oh, look at this. What's that? Tn plus 1 take Tn has to be some common difference for all positive integers n. Just notice, in our work here, this would always be true because n is the term number. You can't have a negative term. So n is a integer, it's a counting number, and natural numbers, if you like, 1, 2, 3. Now, I want you to look carefully at this because this sometimes confuses people. Just remember, Tn plus 1, this subscript is a label for the position of the term, for the position. Where is it in the sequence of terms? Okay, so that means that is the n plus 1th position. Okay, let's look at Tn then. This means the nth position. So can you see that all this is trying to do is, in mathematical language, say that this position is 1 past this one. Okay, so the n plus 1th is further on, 1 position further on in the sequence. And that's a nice little neat mathematical way of saying it without using words. We like to use that precise sort of notation. So what's it saying up here then? It's saying if you take a term and minus the one that came before, you always get D. So it is important in this course to get your head around that. That's going to be quite important shortly. All right, so let's go on and have a look at the name arithmetic. No, it's arithmetic, okay? The arithmetic sequence. Why is it called the arithmetic? Well, let's do a little proof here. There's not much of this in the course. I don't want you to frighten away, but get frightened away from it. But if you say A, B and C are consecutive, that means one after the other, no gaps, of an arithmetic sequence, then B take the one before must equal C take the one before. So we'll get this. Okay, common differences, the difference is D. We don't need to put that here. Okay, so if you rearrange this, add B to both sides, you get 2B. Add A to both sides, you get A plus C. So therefore B, dividing both sides by 2, is a half of A plus C. And this is called the mean, isn't it? The arithmetic mean. There is a geometric mean, we'll have a look at that later. But this is called the arithmetic mean, or the average of terms. So that's where you get the arithmetic sequence. Let's just check it. 3, 5, 7 going up by 2. If you take these two numbers and add them up, then they come to the one between them, because there's equal gaps here of 2 on either side. So 5, the middle term, is right in the middle of the values of the other two. It's the mean of them. Interesting, isn't it, where these names come from? Okay, so you shouldn't just learn stuff off. I want to remind you here of Huddy's hierarchy of learning. Okay, there's the algorithm, or the way in which you do a problem, and then I want you to try to have a more in-depth understanding, and I'll try and do this on the videos to understand the concept, what's going on, and then reach the higher level of, oh, I actually get it, I see it. And so that idea is you're getting up close and personal up here with the actual maths. That's going to make it easier to understand and easier to remember and easier to do. So try and understand here what we're doing and keep it simple and say, what are we trying to do here? What is the real concept? Why are the names like they are? And talk to your teacher about that. Okay, let's go down and see what else we can do. Okay, so let's make a general formula. Is there a way of predicting further down? Let's take this one, 3, 5, 7, 9, 11. If we kept going to the 50th term, could we predict what that would be without putting all the others in? We don't want all these in here. We just want to know what the 50th term would be. Let's see if we can describe the pattern. Well, let the first term be some value A. The next term is A plus a D, the common difference. The next term is plus another D. And the next term is plus another D, and so on. So what's the pattern? To get to any term, call it Tn, you have to get the first term and add on. Now, how many Ds? Here we are at the third term. How many Ds have been added? Well, let's just check it. If we wrote this out, it looks like this. Now, the first term didn't have any Ds added because it's the first term. So the second term had 1 D. And the third term has 2 Ds. And the fourth term has 3 Ds. Oh, the number of Ds is 1 behind the number of terms. Simple idea, because the first one didn't have any Ds. So your first lot of Ds were added to get the second term. And the third term's got 2 Ds. So the number of Ds is 1 less than the number of the term, the subscript if you like. So if I want T50, that'll be the first term, and 50 take 1, so 49D. Okay, so I could, if I knew for my sequence A and D, and I do, A is the first term, plus 49 times the difference is 101. Okay, so it's fairly commonsensical, isn't it? So here's our formula. I'll just scrub that out now. That's our formula there. T equals first term plus n minus 1 by d. Can you see what we're doing? We now have a mathematical model which is a formula to describe the sequence. All right, let's come down and we'll get the statement for that now. From Hayes, there it is. For an arithmetic sequence with first term A, and you can call the first term T1 if you want. I rather like that. And common difference D, the general term, is that. Okay, so we can generate all the terms we like without putting the ones in between. Okay, we go miss a few and go right out to the T100 if you like. Okay, let's do some. So let's have a look at some examples now. So consider this sequence here. Show that the sequence is arithmetic. Okay, let's do that. 9 take 2 is 7. Do the next pair. 16 take 9 is 7. 23 take 16 is 7. 30 take 23 is 7. So assuming the pattern continues, the consecutive terms differ by, remember, consecutive means next to each other, one after the other in sequence. The sequence is arithmetic with the first term, could call it T1, is 2, and the difference is 7. What about the formula? We know for any arithmetic sequence following that pattern, Tn is a plus n minus 1d, a is 2, d is 7, n minus 1 times d. And they put it there so that you can expand this and simplify it down to 7n take 5. That's more convenient, isn't it? So now find the 100th term without all the others in between. So we don't want to keep adding d's and have to do all of them. We can go straight to the 100th term. Look at that subscript, a label for t for term. So it's what? 7 times 100 take 5. So we get this because it's easier than going back to this every time. Okay, so we can use our general term Tn equals T1 plus n minus 1d to generate a particular shorter version, if you like. Okay, now the next two are interesting. Is 828 and 2,341 members of the sequence? Let's see. So if the term was 828, 7n take 5, which is our formula for the nth term, we have to come to 828. Add 5 to both sides, and that would be 7n would be 833, n would be 119. So that is a term, it's the 119th term. Let's check if this could be 2,341. So that means our general expression would have to equal 2,341. Add 5 to both sides, that's 2,346. Divide by 7, To get that value with this formula, you have to go to a value of n, which is 335 and 1/7. That's not an exact term. That's somewhere between the 335th and the 336th term. Okay, so it doesn't fit because you can't have a fraction for a term. N is the term number, and so it's got to land exactly on one of those terms, or in other words, it's not a sequence. It's not separated by the right amount here of 7 to get there. Okay, so n is an integer. Therefore 2,341 cannot be a term. Now that's the basic rule, isn't it? If it's not an integer, and this is Huddy's hierarchy coming in here, if it's not an integer, it's not in the sequence. But do you know why? Because the n value gives you the number of the term. So if we need an n in our formula, 7n take 5, which is 335 and 1/7, we need values in between here, mathematically, to make 7n take 5 equal that. And that means it would not be a sequence because we're talking about the separation of terms exactly by 7. Okay, so that's sort of coming up and unpacking why, if it's not an integer, it will not be in the sequence. Okay, time for you, I think, to have a bit of a go. So here's the next set of problems, 2A2. So question 1 to 3. Pause the presentation and have a go, and I'll show you the answers in a minute. I'll get this last question in. Okay, come down and let's have a look at that then. Question 4. Okay, it's a little bit here. This is a little bit difficult. You'll have to look at the solution for that. Prove that the sequence is arithmetic. Might have to talk to your teacher about that one. It's a proof, so you can't just put in a few numbers. You've got to show that it would be true for all values of n. Okay, let's have a look at the answers now. There we are. Oh, they haven't got the proof there, so you have to check with your teacher on that one. That proof is important. All right, let's keep working on it. We've got some interesting things coming up here. And here's one. Here's a bit more of a puzzle. Find k, given that these are 3 consecutive terms of an arithmetic sequence. Consecutive means they are next to each other. So if we were to write them out as a sequence, you would have commas between them, writing them like that. So since the terms are consecutive and it's arithmetic, this one minus this one, there it is. Watch the bracket because you're taking away 3k plus 1. All of that has to equal this one minus this one. Okay, equating common differences. Okay, so now removing the bracket, that's neg 3k and take 1. That's why you need the bracket. If you're subtracting 3k plus 1, you're subtracting 3k and the 1. And then we have this over here. All right, so we can simplify this. K take 3k is neg 2k. Take 1 equals neg 3 take k. Now, maybe adding 2k to both sides, we get this line, and adding 3, neg 1. So moving the terms around, called transposing terms. Do the opposite operation. Adding it will remove it from that side if it's a neg 3, and here adding 2k would remove it from that side. You have to do the same to both sides, so here it is here. Hope you remember that stuff with equations. So neg 1 plus 3 is 2, and this is neg k plus 2k is k. So k is 2, so that's probably the best way of doing it. Or you could say here, this is interesting, k is the middle term, so it's halfway between the other two terms, because it's arithmetic. Okay, so it's true about any middle term, isn't it? It's the mean of, or the arithmetic mean of the two on either side. So it's halfway between. So you could go to here and then you can solve it. I would not pursue that very much. I think you should understand it, but I think the easiest way is this solution here. All right, are you ready? Because here's your little batch. Okay, and I would do all of these. These are important questions because there's certain little tricks to them, and you have to be careful with the squares here. Okay, might end up getting a quadratic equation you have to solve. That'd be interesting. Okay, so study these carefully. I'm going to show you the answers now. And there we have it. There are the answers to that little set. So here we've got, I told you about the quadratic. Check that you got 2 answers here. Okay, let's move on and do some other little variations, little puzzle type ones. Okay, find the general term for an arithmetic sequence given that the third term is 8 and the 8th term is neg 17. Okay, now this is a bit of a tricky one. So let's go with the third term. The third term is a plus n minus 1 by d, and it comes to 8. Just remember, we don't know a and d. We're trying to find the general term, so we don't know the first term or the difference. So let's do T8. T8 would be the first term plus n minus 1, which is 7 lots of d. That comes to neg 17. And we're using this, of course. Okay, now look out. Maths learning is sequential. This is a Huddyism. Sequential and cumulative. You must learn things in sequence and accumulate your knowledge. And look at this, we're doing modelling, but simultaneous equations has come up. Do you remember that? That you need to be able to do that in maths. So if you multiply this equation by negative 1, you get this. And then if you add it to the other equations, do you notice this is solving simultaneous equation by elimination? Then that will be eliminated, neg a plus a. But you've got to do this multiplication of this equation by neg 1 if you like, or simply subtract it from the other one. So neg 2d plus 7d is 5d, neg 8 plus neg 17 is neg 25, so d is neg 5, adding the equations. So then you can substitute that back in either of the first equations. If we substitute in equation 1, it's a plus 2 by neg 5 equals 8, and therefore a is 18. And then you should check it in the other equations, but here we're going to write the general form. So you should check it back in T8 particularly. Here it is here, and make sure it works. Now the general term, it says find the general term, so the general term is a plus n minus 1 by d, and we can put our a and our d in there, expand the brackets, and get a simpler general term there. And then check it as we've got over here for those other terms, T3 and T8. All right, so that's an interesting little trick. In this course, if you're allowed to use a calculator, I'm going to talk about the Casio 9860 Plus, so that's a good calculator. You could go to Equa mode, and then for equation solving, Equa and go simultaneous and two unknowns, and you could put these equations in. So the first one would be 1, 2, 8, and the second one would be 1, 7, neg 17, and it would solve it for you. So it depends on whether the question says show algebraically or without technology. Otherwise, this would be a way to go. Do it on the calculator. So just check that. Okay, are you ready? Here we are. We've got some funny business here. Look out for fractions. Be careful there. Okay, and using the same sort of approach. All right, let's go down now and have a look at the answers. There are some answers for you. Now, I guess you're getting pretty tired now, but there's not much further to go. Let's have a look and see what we've got. Okay, here's another one. List 4 numbers between 3 and 12 so that all 6 numbers are in arithmetic sequence. So let's go back to basics. The numbers will be 3, 3 plus d, 3 plus 2d, 3 plus 3d, etc. So all 6 numbers. So there is another way of doing this. We'll keep it simple. We'll do this. You could go back and do it like the way we did it before. T1 or A is 3, and A 8. What do we got? No, we've got 6 numbers, so T6 is 12. So you could work with a formula and do that and say T6 is 3 plus n minus 1 by d, and so on, and work with that, and 6 is 12 here. Okay, and 3 plus, here the 6 is 5d, so this is 9 equals 5d, 9 over 5 equals d, or 1.8. So you could do it the way we did it before, or just lay them all out like this. So either way. So 3 plus 5d is 12, and 5d is 9, and then 1.8. So that's another way of thinking about it. So what are the terms? List them now. It's 3, add 1.8, 4.8, add 1.8, 6.6, and so on. Okay. All right, little tricky do's just to see if you can get your head around the basic idea and be able to work with it. Okay, let's have a look. That's gone badly there, so let's have a look. We're too far ahead. Here's your little set of problems. Okay, so there we have it. Have a go, and just be careful with the fractions, and I'll show you the answers now. Okay, 7, 8, and 9 there. So see what you think. All right, I think you already had a glimpse of what we're going to do next, and that was geometric sequences. And I go back to this idea, and I think I have let the cat out the bag here. Don't know what the cat was doing in the bag. Shouldn't put a cat in the bag. Anyway, here, what was happening? I multiplied by 1.07 to increase 1,000 by 7%. And then if this was compound interest, I'd have the same 7% added, and so on. So the geometric sequence has what? We have a multiplier here, a constant multiplier, if you like, or one is a ratio over the other, which is the same multiplier, or a common ratio. So here the sequence is geometric if each term can be obtained from the previous one by multiplying by the same non-zero constant. That constant multiplier, as in compound interest. That's an immediate one you can think of as an example of a geometric model. Okay, geometric sequence. Okay, so here we are. Here's some more. You multiply 2 by 5 to get 10, and then 10 by 5 to get 50, 50 by 5 to get 250, and so on. Now, so that means it's geometric, but notice here, this is the ratio idea, a common ratio. And we're going to use that in the formula, so this is probably a better way of thinking about it. Any term divided by the one before has to have the same ratio. So 50 divided by 10 is 5. 250 divided by 50 is 5. So that's a common ratio idea. And the way we structure the formulas for this one, our mathematical model is going to be a formula again, then that's the way we talk about it, a ratio. It has a ratio. Okay, let's come down and have a look at the algebraic definition. So here it is here, this little bit. So it's geometric means the ratio of any term, notice that subscript again, Tn plus 1, over the preceding term, right? N is the one before n plus 1. That's going to have a common ratio. Okay, so that multiplier is not the way we generally think of it. We think of it as any term divided by the one before. Just remember, any term, if we call it n plus 1, the one before is n. Okay. All right, so here we are. It's geometric with r is 5. That over that equals that over that equals that over that. Neg 10 over 2 is the same as 50 over neg 10, same as neg 250 over 50. Ratio of a negative here, negative 5. Ratios can also be fractions. It could be anything coming out of that ratio. So remember, it's r is a term, any term, divided by the one before it. And just remember, our notation is if that's m plus 1, it's Tn. Or you might like to say if this is Tn, the one before it is Tn take 1. That'd work too, wouldn't it? Okay, using our subscript as meaning the number of the term or the position of the term, position of the term. So if you're at the n position, what's before it? N take 1. If you're at the n plus 1 position, before it is the n. Okay, get the idea. Interesting jargon there, interesting notation. Okay, where's the geometric name come from? So if A, B and C are terms next to each other or consecutive terms of a geometric sequence, then B over A has to equal C over B. So if we multiply here by AB, that will cancel, you get B squared, multiply this side by AB, that will cancel, you get AC. And so B is plus or minus the root of AC. And I don't know whether you've ever had this, but the root of AC is the geometric mean. Geometric mean is when you find the square root of the product. Okay, so now the term in the middle here is the geometric mean of these two. So B is the square root of the product of the two next to them on either side. We won't use that much. We don't talk about geometric means much, and that's not going to be much use in our problem solving. So it gives you an idea of where the name came from. I think it's important, isn't it? Get up close and personal with maths and say, well, he's talking about a geometric sequence. Why is it geometric? There's no geometry in it. There you go. So let's have a look now. And here's our trying to devise a expression for the general term. So how does it work? It goes A, then you times it by r squared, r cubed, etc. Can you see the same sort of things happening? You start with the first term, A, or T1, and then you multiply by r to what power? How many times? It's one less than the subscript. Why is that? Because the first term has no r's. The second term has one r. The third term has 2. Can you get the idea? So it's n take 1. It is 1 behind the number of the term because the first term didn't have any r's. Let's take an example. T50 would be the first term, r to the 49. T100 would be the first term times r to the 99. Okay, get the idea. All right, so let's have a look and do some in a minute. For a geometric sequence, the first term a and common ratio r, the general term is a by r to the n take 1. The power of the ratio is 1 behind the number of the term. All right, let's do some. Here's an example now. So for the sequence here, show that the sequence is geometric. We'll do our ratios. 4 over 8 is a half. 2 over 4 is a half. A half over 1 is a half. So if the pattern continues, consecutive terms have a common ratio of half, there's our geometric sequence. First term 8, or T1 equals 8, and r is a half. So now find the general term. So the general term is this one. So we'll put 8 in front there, and r and n take 1. Okay, so can we simplify this? Yep. 8 is 2 cubed. A half is 2 to the neg 1 raised to the neg 1. So it's 2 cubed. 2 to the neg 1 raised to the neg 1 is 2 to the, multiply that. Neg 1 by n take 1. Remember the power rule. Come over here. A to the m all to the n is a to the mn. Okay, so now it is 2 to the 3 plus this is 4 take n, simplifying it. So using that, can you find the 12th term? Okay, so it's 8 by a half to the 11th. And we can do it in fraction land there without the calculator. All right, well, 2 to the 11th, you probably need a calculator for that. Okay, get the idea? Same sort of stuff, trying to model, trying to find out what's the best description mathematically of patterns that we see. Okay, so I want you to use those ideas to do these 5 problems. I want you to pause the presentation, have a look, have a go at one, and then toggle forward and just check the answer. Do not perpetuate an error. Okay, make sure you check ahead and that you're getting them right. Okay, I'll show you the answers now. Well, here we go. Okay, those 5. See what you think. All right, let's go on now and look at a couple of other examples, then we'll finish up shortly here. Okay, so if these are consecutive terms, what can you say? This is a bit harder. 2k divided by the one that came before. 21k, 21 take k divided by the one that came before. Now have a look at this. We've got to multiply by the common denominator. So the common denominator is 2k, k take 1. So that becomes 4k squared. And multiplied by 2k, k take 1. 2k's cancel, 21k by k take 1. Now we've got to expand this with FOIL, first outers, inners, last. So do that, 21 by k, and take 21 and so on. So now collecting terms up, adding k squared to that side. The k's here, 22k, adding those up and moving across the other side, and then 21. So we've then got to do factorising. Or you could use the formula for the roots of a quadratic. So here, I'll use it in x land. X is neg b plus or minus square root of the discriminant over 2a. You could use that, or the calculator. Okay, to solve that quadratic equation. Again, in equa mode, you could do polynomial and degree 2. So here we would have, when this is 0, k is 7 over 5, or by null factor law that could be 0, so k is 3. All right, so there we've got 2 possible values, and if you put k as 7 over 5, these are the terms you get. K take 1, 2k, and 21 take k, and then if k is 3, put it back in the beginning, you get that. and you get two different ratios for that. Okay, and that, you're getting two possibilities because of this quadratic being formed up here. All right, do you want to have a go? See what you think. So here's question 6. And we're nearly at the end here, so pause it. I must have a go at all of these, I think, for the practice, and because some of them are going to give you quadratics. Okay, let's have a look at the answers. There it is. A couple of possibilities for some of those. Okay, let's finish off with just another little tricky-do problem here. Again, like the arithmetic ones, we're given two terms in the geometric sequence. Find the general term. So here we are. T2 will be AR to the 1, and that comes to -6. T5 will be AR to the 1 less power, AR to the 4th, and that's 162. Now, how can, and we're using this here, how can you actually solve these? Well, because they are power expressions, let's divide them. AR to the 4th over AR, the A's cancel, like the elimination in the arithmetic. So we've got R cubed is 162 over -6, or -27. And of course, I've chosen an easy one here. The cube root of -27 is -3. Just remember, cube root is that number multiplied by itself twice here, or 3 terms, to give -27. Okay, so R is -3, and so taking it back up to the first equation up here, you can say A by R to the 1 is -6, so A is 2. So the general term is T1, or A, by R to the n take 1. All right, your turn, and then you can have a rest. Okay, so here we are. Question 7. Need to do all of these because they're all slightly different. And I'm going to show you the answers now. Okay, so there's some little answers for you. And I hope you're enjoying yourself. Go back over it, make sure you understand what we're doing here. And that's all I'm going to do with you now. But we'll catch you in a later presentation. This is an interesting area. So cheers for now.